In this video, we will discuss about find median from data stream. The median is the middle value in an ordered integer list. If the size of the list is even, there is no middle value and the median is the mean of the two middle values. Implement the media finder class. Media finder initializes the media finder object. Void add num adds the integer num from the data stream to the data structure. Double find mean returns the median of all elements so far. So what they are saying is that we need to implement the median finder class. Now in this, we need to implement two things. First is the add num and second is the find median. So what is happening is that whenever add num will be called, we will receive an integer, right, which will be added into some data structure. So basically this is kind of a data stream that we are getting. That first we are getting 1, then 2, then 5, then 3, right? Then whenever find median is called, we need to find out the median of all the elements that have been added to our data structure till now, right? So if you will see here in this particular example, first we got 1. So I'll just write it here. So we are having 1 right now. Next is called add num 2. So we have got another number that is 2. Next we have got 5. So another number is 5. And then we have got 3. So the next number is 3. Right? And then find median is called. So then that means we need to find out the median of these many elements. Now, how do we find out the median of all the elements? So firstly, we have to take all the elements in the sorted order, right? So the sorted order will be 1, 2, 3, 5, right? Then when the number of elements are odd, then whatever is the middle value, that is your median. And if the number of elements are even, then in that case, whatever are the two middle elements, the mean of that is your answer, right? So basically in this case, if you see, the length is even, the number of elements are even. So we will take two middle values. The two middle values are 2 and 3. So median in this case will be 2 plus 3 divided by 2, which is 5 by 2, that is 2.5. So this is going to be our median in this particular case, right? So now the simple approach what we can follow is that we can maintain an array, right? All of these numbers we can maintain in an array, and then whenever find median is called, what are we going to do? We will need to sort this array. Once we will sort this array, we will get a sorted array. Now in this, we can check that if the length of the array is odd, then whatever is the element present at the index length by 2, that is going to be our median. Otherwise, through that index itself, we can take the two middle values and we can apply the formula and find out the median, right? But in this particular case, the problem is sorting the array every time whenever find median is called, right? Because that is going to increase our time complexity. So we want to avoid sorting our array again and again whenever find median is called, right? So we will have to use some kind of data structure which already stores all of the numbers in sorted order, right? If we will do that, then there would be no need of sorting the numbers again and again when find median is called, right? So for that, what we can use a priority queue, a heap, right? So let us suppose that I am taking a max heap, okay? Just assume that we are taking a max heap. So what you will do, initially it will be empty, right? First you will get 1, so 1 will be pushed here. Then you will get 2, so 2 will come here. Then you will push 5, so 5 will come here. Then you will push 3, so 3 would be here. Because this is a max heap, so it will always keep the maximum value at the top, right? Now our elements are in sorted order. But now when find median will be called, how are you going to access the middle elements of the heap? You will have to first pop these out, right? In the array, we were able to find out those numbers in constant time, right? But here you will have to first pop the extra elements from the heap, and then you would be able to access the middle elements to find out the median. So this is also adding some time complexity to our code, right? So can we try to get the middle elements in constant time? So see, what we can do is that the numbers that you are having over here is 1, 2, 3, and 5, right? What you need for finding out the median, you always need the middle element, right? So what I am saying is that your numbers were 1, 2, 3, 5, right? You always need the middle elements for finding out the median, right? So there are two cases. One is when the number of elements are even, which is this particular case, and another is when they are odd. So let us suppose 1, 2, 3, 4, 5. This is the case, right? So what we can do is we can split these numbers into two. into 2 meaning I am saying I will split these numbers, right? I will keep these many numbers in a separate data structure and these many numbers in the separate data structure, right? Then what will happen is, if I keep this in a separate data structure and I take the maximum value from this, right? And I keep these elements in a separate data structure and I take the minimum value from this, then I will be able to get the median in constant time. If I choose some data structure which gives me the maximum element from these elements in constant time, then I will be able to identify my median in constant time, right? So this is the happy case where the number of elements are even. So we can put these many in separate data structure and these many in a separate data structure, right? What if our number of elements are odd? In that case, in one of the data structures, we can keep less number of elements and in the other one, we can keep more. So basically in one, I can keep these many and in the other, I can keep these many. Or we can also put these many elements in the first data structure and these many in the second data structure. Then how will you identify the median? That whichever data structure is having more number of elements, take the value from that data structure. So in this particular case, this is having more elements, right? So you will take the maximum element from this, which will be 3. And if you have kept 1 and 2 in one data structure and 3, 4 and 5 in a separate data structure, then in that case, since this is having more number of elements, so you will take the smallest value from here, right? So what we are saying is that we will be maintaining 2 data structures, right? So the point to be noted here is that in the first data structure, I always want the maximum value, and in the second data structure, I always want the minimum value, right? So can I take one max heap and one min heap, right? So what I am saying is that we will take 2 heaps. One will be a max heap, let's denote it with maxi, and another will be a min heap, let's denote it with mini, right? So these will be our 2 heaps. So what we will do is that all of these left elements we will keep in the max heap and all these right elements we will keep in the min heap, right? So that we can identify the maximum value from the max heap and the minimum value from the min heap, right? Now, how are we going to push elements into our heap and how are we going to maintain consistency between them? Consistency meaning that 1 and 2 should be present in maxi and 3 and 5 should be present in mini, because we do not know in which order the elements are coming. So see, because we always need to find out the median, which is always the middle element, right? So what we will try to do is that we will try to keep the size of maxi and mini equal if our number of elements are even, right? When I am having 4 elements, then I will try to keep 2 elements in maxi and 2 elements in mini, so that the top 2 values from these two gives me the median. And when my number of elements are odd, then in any one of them I can keep an extra value or an extra element, right? So that whichever heap is having extra element, I will take the top of it and that is going to be my median, right? So what I am saying is that with respect to the size of maxi dot size will be equals to mini dot size, right? Or another case would be that the absolute of maxi dot size minus mini dot size is equals to 1, right? So basically my 2 heaps are either going to have same number of elements or one of them would be having one extra, right? So if in any case any of the heap is having more than one extra element than the other heap, then we will balance their size, right? Then another thing to notice is that when I am keeping 2 values in the max heap and these 2 values in the min heap, then this max value should be less than or equals to this minimum value, right? Because this array has to be entirely sorted for finding out the median, right? And if I am keeping all the left elements in the max heap and all the right elements in the min heap, then whatever is the maximum value in the left, that should be less than or equals to the minimum element in the right, right? So basically all the elements in maxi should be less than equals to all the element in mini, right? So another condition is that maxi dot top should always be less than equals to mini dot top, right? So keeping these two conditions in mind, one for the top element and one for the size, we will push elements into our heaps right? And we will try to find out the median. So what we will do is that whenever we will have to add a number into our heaps, we will always add it in the max heap, and then we will check whether any of these conditions are violated. And if any of these are violated, then we will try to satisfy them by balancing our heaps, right? So first of all, we have got add num1, so it will be directly added to the max heap, right? Now you will see, is this condition violated? So first we are checking this particular condition, right? Because if this is not satisfied, then we will take the top element from maxi and we will push it inside mini, and that could further violate the size, right? That is why first we will check this condition and after we will check the size, right? So right now maxi is having only one element and mini is empty, so we cannot perform this comparison, so we can skip this condition. Now we will check the size. So here the difference in the size of these two is 1, so this condition is satisfied, then that means we can move forward. So next we will have to add 2 into our max heap. So 2 would be added here. This condition again we cannot check because mini is empty, but then we can check the size. Now size is not equal and the difference is also not 1, it is 2. The size of max heap is 2 and min heap is 0. So then that means we will have to balance the size of our heaps. In that case, what we will do is that we will pop the top element from maxi and we will push it inside mini, right? So whichever heap is having more elements, from that we will pop an element and we will push it into another heap, right? So 2 will be popped from here and it will be added into mini. Next the number will come as 5, so 5 will be added here. Then we will check this particular condition. Now you will see that 5 is not less than equals to 2, so this condition is violated. So then that means we will have to pop this 5 from maxi and push in mini, right? So 5 will be removed from here and added here, right? And since it is a min heap, so these will be sorted like this, right? Now you will check the size. So size maxi is 1 and mini is 2. The difference is 1. So size is not violated, right? So next the element will come as 3. So 3 will be pushed here. Now we will check this particular condition. Now 3 is not less than equals to 2. So the condition is violated. So we will pop this 3 and we will push it inside mini, right? So it will look like 2, 3, 5. So these will be our heaps. Then we will check the size. So maxi's size is 1 and mini's size is 3. The difference is 2, which is greater than 1. So we will have to pop an element from the heap which is having extra elements, right? So we will pop this 2 and we will push it inside maxi. So this 2 will come here now. Next we have called a find median. So now you can see that okay, both the heaps are having same size, then that means we are having even number of elements. So we will consider the top elements of the two heaps. We will take them, we will sum them, we will divide them by 2, and whatever we will get, that is going to be our median, right? If in case, let's suppose here we had a 3 and then you had to find out a median, so you would check that okay, the size of maxi is greater than the size of mini, so whatever is present at the top of maxi, that is my median, right? And the other case is that 3 was present here. So in this particular case, the size of mini is greater than maxi, so whatever is at the top of mini, that is going to be by median, right? So this is how we are going to solve this problem. So if you see, pushing and popping into heap takes log n time, right? That is of order of log n, right? And accessing the top element is in constant time, right? So here we do not have the need of sorting our array again and again, and we are also able to access the middle values in constant time. So we have optimized our approach very much. So let's quickly look at the code to understand in depth. So first of all, we would be needing the two heaps. So we will create a priority queue. So in C++, heaps are implemented using priority queue. And by default, priority queue creates a max heap, right? So we want one max heap and one min heap. So the max heap we have already created. Now for the min heap, there is a different syntax which is as follows. So this is the syntax for creating a min heap. So this will be our mini, right? So we have created the two heaps. Now whenever the add num is called, we need to add the number into our max heap, right? So in maxi, we will push num. Now once we have pushed it, first we will check the condition that the top element of maxi should be less than equals to the top element of mini. If it is not, then we will have to push and pop, right? So we will check that. Now it might be a case that mini is empty. in any case, or max is empty, right? So we should also check that if mini is not empty and maxi is not empty, right? Then only check. What do you check? If the maxi.top is greater than mini.top, then that means our condition is not being satisfied and we will have to do the push and pop operation, right? So first let's take the top value of maxi. So it will be maxi.top, and then we will pop it from maxi, and then we will push it into mini. So mini.push val, right? We can also write it in two lines. We can write mini.push maxi.top, and then we can pop it from maxi. So that way also it is possible. After we have checked this condition, now we need to check that whether the size of our heaps is balanced or not, right? So first let's check that if mini dot size is greater than maxi dot size plus 1, right? Meaning the difference between the size of the two heaps is greater than 1. Then in that case, since we have kept this condition, so mini would be having more number of elements, right? So we will have to pop from mini and push into maxi, right? So we will take val, this will be equals to mini dot top, then we will pop it from mini and then we will push it into maxi, right? So this is what we are going to do. Then we will check that if maxi dot size is greater than mini dot size plus 1, because any of them could be having more number of elements, right? So we need to check both of them. So we'll take the top value from the maxi in this particular case, right? And then we will pop it from maxi and then we will push it into mini, right? So with this, we have implemented our add num. Next, let's implement the find median. So in find median, just we need to consider our top elements on the basis of whether their size is odd or even, right? So what we can check is that if mini dot size is greater than maxi dot size, then that means we are having odd number of elements and mini is having more number of elements, right? So in this case, we will return mini dot top, right? Else we need to check that if maxi dot size is greater than mini dot size, then that means there are odd number of elements, but maxi is the heap that is having more number of elements. So we will return maxi dot top, right? Otherwise, if both the conditions are not satisfied, then that means both heaps are having equal number of elements. So we will return the mean of the top elements, right? So we will do mini dot top plus maxi dot top, and this has to be divided by 2.0. We need to return double, that is why we are dividing it with 2.0. So let's run this. So our test cases are accepted. Let's submit this. So it got accepted. Thank you so much for watching. Please like the video and subscribe our channel.